Welcome back to the shop, everybody. Today we're going to be doing some screwed up experiments. Which one of these two screws would make more power? This large 3-inch diameter screw or this much smaller 1-inch? We're going to find out the answer by testing these 4 screws. I'm working on a project and I need to know what screw will work the best. These screws have the same 5 threads per inch, which means they will move the same amount with every turn. By only changing the diameter of the screw and applying the same amount of torque, how does this affect the power? So we're going to build a little rig, we're going to put a meter underneath it, we're going to collect some data, and see which one makes more power. Here's the machine that we're going to be using to test these screws. I started off with 2 pieces of plate steel that I had here in the shop. Waterjet, this interesting design. The press going to allow me to control each one of these screws in an environment that we can collect some data from. I just undo these 4 bolts. I can spread the 2 sides apart and then throw in a new nut that's been welded to one of these plates, and then it gets sandwiched together and we can exchange screws out rather quickly with this design. And then the screw will be pushing down on this electric meter that's going to give us a readout and calculate how much force that we're applying with the same amount of input, which will be provided by this torque wrench at 50 and 150 foot-pounds of torque, hopefully getting some dramatically different results. We'll be testing the 1-inch screw and of course the 3-inch screw, and I added a 1.25 inch screw and a 2-inch screw into this mix just to see if our results are consistent. That's how the rig works. So there are pros and cons to each one of these diameters. Let me show you what I mean. The screws will have a constant 5 threads per inch, so if we take an equal length section of them and unwind the threads, you'll see an inclined plane. The angle of the plane is determined by the diameter of the screw. The large diameter will have a nice taper to it, so if I shrunk myself down and rode a bike up it, it'll be a nice gradual ride up the ramp. And the small diameter will be a lot shorter and therefore a lot steeper. Riding my bike up it will be a lot more difficult. This demonstrates the efficiency of mechanical advantage, and the small angle results in an easier turn. Now let's add friction to the equation. Friction comes from how much surface area the screw's threaded spindle is in contact with the nut. So there will be less friction on the small diameter screw and more friction on the large diameter. Ultimately, it's a test of mechanical advantage versus friction. The small screw will have less mechanical advantage but less friction, and the large screw will have more mechanical advantage but more friction. What will output more force? Now that we're ready, let's do some shop science. Shop science. All right, enough screwing around. Let's get this test started. The first test we'll do is use 50 foot-pounds of torque, starting with the 3-inch diameter screw. I'm going to remove some human error by performing this test 3 times and taking the average of the 3 results. Oh man, 2,085. That's pathetic. Very good results here. 2,074. 2,135. That test is only resulting in an average output of 2,098 pounds of force. Let's see if our next screw can do better or worse. So let's test the 2-inch screw with 50 foot-pounds of force. The 2-inch screw's average output of force is 3,222 pounds. Let's move on to the 1.25 inch screw. 3rd time's the charm. Applying the same 50 foot-pounds of force generates us an average of 3,352 pounds for the 1.25 inch screw. Now for the 1-inch diameter screw. The same 50 foot-pounds in gets us an average of 4,847 pounds. At these lower input levels, we can obviously see that friction is affecting the screw more than mechanical advantage. But I'm a little bit curious to see what happens when we crank up the torque to 150 foot-pounds and see how it changes our results. Let's commence with the 3-inch screw test at 150 foot-pounds of input. We've got some interesting results. 150 foot-pounds is giving us an average output of 6,208 pounds. So let's move on to the 2-inch screw. We've got an average result of 9,060 pounds. The 1.25 inch screw is up next. We finally break into 5 digits, with the screw giving us an average output of 12,389 pounds. And now the 1-inch screw. So that averages 13,398 pounds. What I'm seeing is that friction is still playing a huge role, almost tripling the previous tests. So I have an idea. Let's change a variable to see if we can reduce some of the friction. Let's talk about the nut and screw a little bit. A typical nut for a screw is as tall as it is wide. So this being a 3-inch, this is 3 inches tall. 2-inch tall. 1.25 inches. This has a 1-inch. It's kind of on a uneven playing field. So let's reduce some friction, because we know that's the enemy, and make all of these 1-inch nuts. Let's see if we can remove some of the friction from these screws and see what kind of results that we can get from that. I'm really curious to see, by removing up to 2/3 of some of these nuts, how much it's really going to affect the output. We could be reducing friction, but we're also going to be increasing the load on the leftover threads. Will this have a positive or negative effect on the force? We've now leveled the playing field with all the nuts being 1 inch tall, so we won't need to replicate the 1-inch screw test. We will start with the 50 foot-pounds of force into the 3-inch screw. We've got a slight jump in force output with an average of 2,344 pounds. Now for the 2-inch screw with the 1-inch nut. The reduced nut on the screw gives us an average output of 3,154 pounds. And for the shortened nut on the 1.25 inch screw. And this gets us an average of 3,306 pounds. What we can see here is the nuts that have been reduced by over 50% have seen a gain in force. I'm actually surprised, and I find this quite unexpected. Let's see if that finding remains consistent when we dial up the force to 150 foot-pounds. Cut nut on the 3-inch screw. It gives us an average result of 6,412 pounds. The 2-inch screw is up next. And it results in an average of 8,455 pounds. And now the 1.25 inch screw. That's better. Its average is 12,784 pounds. By removing some threads that come into contact with the screw, it does change the output force. I believe weakening the nut is probably not worth the extra force. Let's add a grease test to this whole thing to really round off this whole experiment and see what happens. 50 foot-pounds of input on the 3-inch screw with this short nut, and the grease added coming right up. Its result is an average of 2,228 pounds. Bringing it down to the 1-inch screw with the lubricant. And the average is 4,963 pounds. These results are pretty similar to the dry thread results. We probably didn't see a big difference because the Acme thread is already an efficient, low friction thread design. So let's jump up the torque to 150 foot-pounds of input. Greased 3-inch screw, still in its 1-inch nut. It gives us 6,339 pounds as its average. And finally, the 1-inch greased screw with 150 foot-pounds of input. Averages out to an astonishing 16,444 pounds. What I really notice is that the grease really isn't affecting these larger diameters that much, which is quite a surprise. But on the 1-inch screw, there is a huge improvement by adding grease. Well, thank you guys for joining me on this cool little shop science experiment. I know I learned a ton, and I will be applying all this information on the latest and greatest build that I'm working on, so stay tuned for that. And I know before you guys go, you're gonna ask, do I have drawings for this cool little shop press that I built here in the shop for the experiment? And yes, you guys can go to the Fireball Tool website and download it for yourself. So until then, I'll catch you guys on the next one.